So the objectives is to identify the compositing rule, then how to use the clipping path, to apply fonts and font matrix, and at last to understand glyph, ligature and derived fonts. Transparency and compositing rule. Compositing rules determine the results of rendering overlapped objects, where there is intersection between two or more objects. Various visual effects, such as different degree of transparency, can be obtained by choosing compositing rule. To establish the compositing rule, the concept of alpha channel is needed. The alpha channel can be viewed as a part of color properties that specify the transparency. So, an alpha value is a number between 0 and 1, with 0 represents complete transparency and 1 complete opaqueness. The Porter-Duff rule can be derived systematically from a probabilistic model. The alpha value of a color can be interpreted as the probability that the color will be shown, or more concretely, as the portion of the pixel area covered by the specified color. To combine the source and the destination colors with their respective alpha values for different cases need to be considered. First, source color occurs only, where second, destination color occurs only. Both colors occurs only, neither of the colors occurs only. The following figure can illustrate the four events where occur with a probability. If the source occurs only, then alpha s for the source into 1, and so we subtract the probability of alpha d, then the SRC will appear only. For the destination region, where the alpha d, the destination will appear only, then alpha d multiplied by 1 minus alpha s to remove the source. Both colors occurs where is the intersection, which means alpha source with alpha destination. Neither of the two colors occurs is where in this region, where it is 1 minus alpha s into 1 minus alpha d. A compositing rule simply decides whether to retain a color when the color occurs. In the source color only event, a rule can choose to retain the source color or to omit it. In the destination color only, the destination color can be selected or omitted. In the both color events, a rule can choose the source color, the destination color, or no color. So, in the neither color event, a rule can only select no color. Therefore, the total number of rules is 2 multiplied by 2 multiplied by 3 multiplied by 1, which is the 12 Porter-Duff rules. Here we will see in the following table the 12 Porter-Duff rules having the following f source and fd coefficients. For example, in the source over rule, we choose the source color in the event of the source color only and the event of both colors. Source over, then we want to see a complete source where f source should be 1. It chooses also the destination color in the destination color only, which means we want to see only in the destination color the destination region without the intersection. Then we can choose FD as 1 minus alpha s. it must choose no color in the neither color event as we said in the destination color. Consequently, the probability of source color occurring in the combined color is alpha S into 1 minus alpha D plus alpha S alpha D should equals to alpha S. And the probability of the destination color is alpha D into 1 minus alpha S. This leads to the selection of the coefficient Fs equal 1 and Fd equals to 1 minus alpha d as shown here in the table. Here is some examples on the Porter-Duff rules. We choose 6 examples. As we can see here, source over implies Fs will be 1 and Fd will be 1 minus alpha S. Where here is destination order over, then Fd will be 1 and Fs will be 1 minus alpha d. Here we want only the intersection but with the source color, which means source n, then Fs will be alpha d and Fd will be 0. And destination n, then alpha s will be Fs will be 0 and Fd will be alpha s. And source out, then we want only the source without the intersection. Then we will use Fs, which is 1 minus alpha d, and Fd equal to 0. And destination out, then we want to see only the destination part without the intersection. Then Fs will be 0 and Fd will be 1 minus alpha s. Early versions of Java 2D support the first 8 rules in the table shown in the previous slides. Starting with G2 SDK 1.4, all 12 rules are supported. The alpha composite class encapsulates the rules. An instance of alpha composite for a rule can be obtained by a static field of alpha composite with the name shown in the previous table. To apply a compositing rule to a graphic 2D object, simply call the setComposite method. For example, the following statements set the compositing rule to source n alpha composite dot get instance of get rule comma alpha. Then to apply a compositing rule using source n, G2 on graphic G2 dot set composite alpha composite dot source srcn. In this example, we want to calculate the alpha value and the color value of at a certain given a certain rule. So if the RGB and alpha values of a source pixels are 0.5, 0.0, 0.8 and 0.4 respectively, and the values for the destination pixel are 0.2, 1.0, 0.5 and 0.6 respectively, find the RGB and alpha value of composite using source over rule and destination out. First, as we read here, RGB and alpha value, then 0.5 is for the red, 0.0 for the green and 0.8 for the blue, and the alpha value is 0.4. These are for the source pixel. For the destination, 0.2 is the red, 1.0 is the green, and 0.5 is the blue, and the alpha value is 0.6. So we want to find the equivalent RGB and alpha value for the two cases. First, we will work on source over. For the source over, we have the general formula alpha C equal Fs alpha SCS plus Fd alpha D CD. For the source over, we can see that Fs should be 1 and Fd should be 1 minus alpha S. Fs should be 1, we substitute instead of it 1, and instead of Fd 1 minus alpha S. Alpha S 0.4, then we put here 0.4 times RGB of 0.5 times 0.8. And also if we continue for 1 minus 0.4 alpha S times 0.6 for alpha D, RGB of 0.2, 1, 0.5. Then we multiply 0.4 by each of the following coefficients, and 0.6 times 0.6, which is 0.36, multiplied also by each component here, and then we try to add the same colors with each other to get this equivalent color. Then if we want to calculate for alpha for the source over, we substitute Fs with 0.4 and Fd with 1 minus 0.4, and we calculate the alpha equivalence, which is 0.76. For the destination out, we can also calculate the Fs, which is should be 0, and Fd should be 1 minus alpha S, and we apply the same calculation to obtain alpha color and the alpha value. Okay, this example illustrates the application of the alpha composite class to implement Porter-Duff rules. This example shows several visual objects rendered with the 12 different Porter-Duff rules. The rules are selected by clicking the mouse on the display. If we see this program demonstrate the 12 Porter-Duff rules, the class compositing extend the G-panel class and implement the mouse listener interface. The list of compositing rule is placed in an array of array using the constant defined in the alpha composite class. The variable rule index points to the current compositing rule. The mouse clicked method rotates the compositing rule by implementing the rule index. A repaint method is called to refresh the display with the new compositing rule. So every time the panel is clicked, the panel switch to a different compositing rule. Here is a part of the code. If we want to see the whole code, we can refer to our book page 83. So in the constructor of composite panel, an image is loaded from a disk. In the paint component method, the image drawn first. The composite rule is then set to the current compositing alpha value with an alpha of 0.4. Using the static method getInstant of the alpha composite class, a red circle is drawn and the string Java is also drawn with a white color. The on-screen drawing surface does not maintain alpha channel itself, and the alpha value of any pixel is always implicitly assumed to be 1. Consequently, as soon as an object is painted to the screen, the destination alpha becomes 1. Because of this behavior, some of the compositing rules don't produce interesting results. For example, the rules destination over, destination out, destination top, and XOR will always ignore the source, since the destination alpha is 1. One way to show more interesting effects is to draw on an off-screen image with an alpha channel. Here we can see the sample of the output of a previous code. We can run we can take the full code from our book and run the code on the NetBeans to see the different results. Each time we click a mouse, we will see a new result with a new rule, Porter-Duff rule. Clipping path. The rendered image may be clipped by a clipping path. A clipping path defines a region in which the object will actually be visible. Graphic 2D maintains a current clipping region. When an object is drawn, it is clipped against the clipping path. Portion of the object falling outside the clipping path will not be drawn. Any shape object can be used for clipping, as we can see here in the example. A clipping path defines a region in which the object will be visible, so the portion falling outside the clipping path will not be drawn. This is the clipping path, as we can see here. So the following code segment sets an ellipse at the clipping path and draw an image. Only the portion of the image which lies inside the ellipse will be visible. As we can see here, we create a shape ellipse, which is a new ellipse, and then we apply we set clip using this ellipse, and then we try to draw the image, so only the image part that lies inside the defined ellipse will be shown. Another method of graphic 2D that can change the clip region is void clip shape path. This method will clip the current clipping region further with the specified shape. The following example demonstrates the use of clipping paths. In this simple example, a special shape is created and used as the clipping path for graphic 2D object. The subsequent drawings are clipped by the shape. In the paint component method, a general path object with two line segment and two quad curve is constructed, as we can see here. Path dot move to, then quad 2, then line 2, then quad 2, and at last close path. We will see this, which means this path. Then the closed path is set as the current clip path of graphic 2D object by calling the method clip, as we can see in this line. Then the path is used again with the fill method to show the clip area in a light gray shape. So as we can see here, then we create a color or set the color to 200, 200, 200, which means a gray color, and then we try to fill the path with a gray. Then we try to change the color to black. two graphic objects are drawn, which are a string clip path demo and an ellipse draw string and draw oval. Then the effect of clipping, as we can see here in the output, is obvious. Only the portions of the object lying inside the clip are visible, as we can see here. Text and font. In computer graphics, text represents a special type of geometric object. A text string can be compactly represented by a sequence of characters with standard coding scheme, such as ASCII code or Unicode. The actual rendering shapes of the characters are determined by predefined fonts. A geometry describing the shape of a character is known as a glyph. A font is a collecting of glyphs for an entire alphabet. The relationship between characters and glyphs is not always one-to-one. Sometimes one glyph may correspond to several characters, as in the case of a lecture. A lecture occurs in fonts when certain two-character sequences are rendered in a combined fashion. A common lecture is FI in some fonts, for example. Java 2D offers a rich set of font and text manipulation features. The most common high-level usage of text involves creating a font object and calling the method setFont and drawString in Graphic 2D, as we see in the previous example. A font object can be created with the following constructor: font, string name, int style, int size. The name parameter specifies the font face name or the logical name of a font. A font is identified by the font face name, also called the font name, such as Times New Roman. The fonts available in an environment are platform dependent. Java also support logical fonts to improve portability. A logical font is mapped to a physical font on a particular system. For example, the logical font sans serif is mapped to Arial in a Windows system. Here we can find the 5 logical font families that are supported in Java, like serif, sans serif, monospaced, dialog, and dialog input. Also, we have the style parameter, which is a mask to select font style. 3-bit masks are defined in font, and they may be combined with the bitwise or operator, which are plain, italic, bold. Also, we have the size parameter, which specify the size of the font. A font object can be selected in Graphic 2D object with the following method, which is setFont, font, for example, font. This font will take effect for subsequent call to method for drawing text, for example, draw string, string s, int x, int y, or we can use float x, float y. In addition to applying existing font in the system, it is also possible to derive new fonts from existing ones. We can use the following methods in the font class to generate derived font. As we can see, we can derive font by integer, which is the style, or by float the size, or by style with size, or by using a certain affine transformation, or using a style with an affine transformation. Font metrics are measurements of rendered text with a specific font. The following methods of font provide for metric information, which are get string bound, get a string s and a font rendered context FRC, and return a rectangle 2D. And the get line metric, get a string and the font rendered context FRC, and return the line metric. Because the precise metric also depends on the option of rendering, the above methods, as we see, use a font rendered context object to obtain the additional information. The font render context object can be obtained through a method in graphic 2D. Font render context get font render context. The get string bound return a bounding rectangle for a string. We have also the get line metric method, return a line metric object that contains more detailed line metric data. First, the baseline is the reference line of the font. The ascent is the amount that the font extends above the baseline. The descent is the amount extending below the baseline. And the leading is the extra space between the two lines. We will see in the next slides an example of these methods. The following methods of the line metric retrieve the matrix get ascent, get descent, and get leading. The following example demonstrates font-related feature. The derived font and font matrix are demonstrated in this example. 3 lines of text are displayed. The first line is drawn with a derived font that is slanted to the left. The second line shows the bounding rectangle together with the text, and the third line displays the baseline, ascent, descent, and leading for the text. فإذا here 3 lines of text are drawn in the paint component. The first we set the font to serif bold, and the size is 36, and we make a derived font. As we can see here, an affine transformation is created to perform a horizontal shear. Then a new font is derived, as I said, in 36 point bold serif font with the transformation. The derived font is slanted to the left because of the shear transform. Then the text string, which is a derived font, is drawn using the derived font. A font render context object is obtained from the graphic 2D object. It is used in the method get string bounds of the font object to retrieve the bounding rectangle of the string bound. The string is drawn together with the bounding rectangle, as we can see in the draw and draw string. Then the third line of text is a string baseline, ascent, descent, leading. The baseline of the text is drawn based on the width of the text. The line metric object, as we can see here, for the string is retrieved through the get line metric. Then the values for the ascent and descent and leading are obtained from the object, and the line corresponds to the values are drawn relative to the baseline. Here is the output. As we can see, 3 lines of text are displayed. The first line is drawn with a derived font that is slanted to the left, and the second line shows the bounding rectangle together with the text, and at last the third line that represents or displays the base line, ascent, descent, and leading for the text. Ligature. Java 2D also provide advanced functions for font-related operations. In particular, glyphs of characters in a font can be retrieved as shape objects. This enables sophisticated processing and application of the glyphs to achieve varieties of visual effects. We have a class font represents a font. The class glyph vector encapsulates the geometric description of a sequence of glyphs. So a glyph may contain multiple letters, which is then a common ligature, for example, I. To obtain a glyph vector object for a string corresponding to a font using the method of font, as we can see here, glyph vector gv equal font dot create glyph vector of rfc and string Java. First, the font rendered context object define certain measurements necessary to render a font. It can be obtained from graphics 2D object by calling the method get font render context. Once the glyph vector is created, the shape object corresponds to the glyph can be obtained by the get outline, as we can see here, from the point 0, 100 to 100. So this is a simple example of what we said. Here is an example of glyph. The program shows the technique of retrieving the glyphs of a text string as a shape and use it as a clip path. As we can see, the method is the get outline. The 100 and 200 are the x and y parameters that specify the starting location for the rendering the glyph. The returned shape object corresponds to the glyph can be processed and rendered like other shape objects, which is, for example, shape glyph. So in this program, we display the special figure in a subclass of GPanel. The paint component is overridden to perform the drawing. A bold 144 font, serif font object is created. Then a font render context object is obtained through the graphic 2D object. The glyphs from the string Java are obtained from the font and font render context, and they are kept in a glyph vector variable. Then the glyph vector is converted to a shape, as we can see here, to the shape through the get outline method. Then the shape is set to the clipping path of the rendering object by calling the method setClip of graphic 2D object. 2000, as we can see here, is a for loop from 0 to 2000. Then 2000 ellipses with random location are drawn on the panel. Only the portions inside the glyphs are visible. The text string is never explicitly drawn, but the drawing is inside the clipping region, clearly highlights the outline of the glyph.